Yeah, okay, so I'm standing in front of the first two slides, and there's not a whole lot of content on them, but I want to stay here just for a minute or two to, I guess, outline what this talk is about and how it will be structured. So on the title slide, you should see it's called Quantum Combs, the Min Entropy and Their Uses. And this talk is going to be essentially from left to right through this title. So we'll head towards what quantum combs are. Afterwards, we'll talk about the min entropy. And then afterwards, what both of these things can be used for in conjunction with each other. On the second slide, it should see broad aim. And this is just a very simple slide to say, okay, generally speaking, a very sort of simple sentence, but potentially vague, about what we're aiming for with these tools. So I ultimately want to learn an unknown property of a quantum system by interacting with it. This unknown property is going to be able to influence the quantum state, the static thing that we're interested in, but also the dynamic thing, the evolution of this state. So to begin with, we need some way of representing both of those things in an appropriate way, which is what the quantum comb aims to do. So just one sec. I'll move to the next two slides. So I guess, would consider myself a quantum information theorist these days. So as a quantum information theorist, if I want to represent a quantum state and its dynamics, I open the Bible, which is the Nielsen and Schwung textbook, and I start reading. So if you're looking at the representing quantum states and dynamics slide, you should see that, well, we can represent quantum states as density matrices. This is this rho character here, which is a linear operator on a Hilbert space. I'm taking this to be finite dimensional for the entire talk, just to avoid any pesky problems. And moreover, this operator has it's positive semi-definite, which is this greater than or equal to 0 symbols, and it has trace 1. So I'm kind of hoping that some of this is familiar to people. Quantum operations are going to describe our dynamics, at least for the time being. And these are linear maps. They're trace non-increasing, which is this next sort of condition that I have on the slide. So maybe I can start to draw. So trace maybe not in white. Trace not increasing is this one. And we also have complete positivity, which I've not entirely rigorously denoted with this next condition. So essentially for any positive operator, potentially on a bigger Hilbert space, if we tensor our quantum operation E with the identity on that rest of the system, it's still positive. It still sends it to a positive thing. It's a positive semi-definite thing. Within this textbook, there are a couple of different ways of representing these quantum operations. So I guess the first definition is this top line. This equivalent definition, second equivalent definition, is this next one, where we can represent it with these specific operators EK that satisfy some conditions, or we can represent it on this third line as the trace over some other system, and also with some unitaries involved. Now, this is a relatively powerful formalism, and it's quite useful for a lot of things. As you can see, it says quantum operations include various things, so state preparations, unitaries, noisy channels, measurements. So this is a lot of what we think about. And in particular, with state preparations, as I said before, I want a way of representing a quantum system, both its state and its evolution. So this seems to do both of these things at once. We can represent the state as this quantum operation, there's a state preparation, and also then these various other evolutions there. But if you keep reading in Nielsen and Schwung and you get to section 8.5, it does say that this formalism has limitations. Unfortunately, this is sort of where the textbook stops. And this is where we're going to take off towards quantum combs. So next slide, limitations and resolutions. The main limitation was already written on that previous slide, and I've also written it here. If we take this definition of a quantum operation as a trace over the environment, of some unitary acting on this initial density matrix rho, and also some state of the environment, well, we are implicitly using the assumption that we have a tensor product between these states. So there's a separable state between the system that we're interested in, the system under our control, which is the state of which is denoted by rho, and the rest of the world, or the rest of the whatever we need to do this Stein spring dilation, this is called. So where we have the unitary dynamics and then a trace out of the environment, we are implicitly assuming that we have a separable state. And this is not realistic. It's essentially never the case in a lab that we will have this. It might be pretty close. The correlations between our system and the environment may be quite weak. And so in that case, these CPTP maps, these completely positive trace preserving or trace non-increasing maps, do a pretty good job of modeling what we see, but it's not always the case. And this was actually, I guess, in sort of the early 2000s, this was discussed quite a lot in the literature. In particular, these first resolutions that I have listed there, these came up in a series of papers. It was quite an interesting sequence of replies between two authors, Pachoukis and Aliki, I think, where they talk about what we can give up about the quantum operations, these E's, such that we can solve this problem. We get around this assumption of separability between the system and the environment. One option is to give up complete positivity, but we probably don't want this, right? Complete positivity in a certain sense means that we can map valid probability distributions to other valid probability distributions. We don't have any negative probabilities cropping up, which is one thing that people do look at in quantum mechanics. So maybe we don't want to give that up. We can give up linearity, but again, quantum information theorists, all I want to do is linear algebra and nothing more, so I don't want to give up linearity. And there are a few other things that you can give up that I'm not so familiar with, and you can read the literature if you're interested in those. A better, and I guess more modern resolution is slightly different. So this next line where I say better resolution, the thing inside the trace looks a lot like what's in between the unitaries in the trace on the first line, except now we're not assuming that we have a separable state between the system and the environment. What we are assuming is we have a local operation. So A now is itself some sort of CPTP map, and we're acting on as an identity on the environment. So we have this potentially correlated state, we have some operation that we do, a system, and then we apply the unitaries and you trace out. So what this now is, instead of being a map from a density matrix rho to another density matrix E of rho, we're having a map from some map, a system, to a density matrix. This is sort of the first steps towards quantum combs, because I mean, I guess you can see these two diagrams. The one on the left is specifically describing what I have written in the better resolution, but we can also push this a little bit further. So instead of just having a single operation, a system that goes into this broader construction, we can have multiple different maps that go into this broader construction. And this is another, I guess, limitation of the quantum operations formalism, is that it only maps density matrices to density matrices between two times, so time t0 and time t1, where ultimately a lot of the things we do in quantum mechanics is multi-time, and we want to investigate multi-time correlations, which is something native to the quantum combs formalism. I can't remember if I said at the start, please ask questions throughout. I'm happy to field them.
Will do.
All right, so we move on to these next couple slides. So before we get to the quantum combs definition that I would like to present, I want to talk a little bit about the joy operator. Again, this may be familiar to people if you're familiar with quantum information theory. It is used quite a lot. And I think the concepts here also be familiar to people within this community, especially if you're familiar with some category theory. So essentially what we're doing on this slide is we're replacing, or we're mapping this quantum operation E, which is a map, to some state, essentially. I mean, it's some operator, some linear operator, but it's going to, instead of being an operator between this set of linear operators on the Hilbert space A to the set of linear operators on the Hilbert space B, it's going to be represented by a linear operator on HA tensor HB. The way we do this, we first need a different Hilbert space HA prime, isomorphic to HA, again, finite dimensional. And we need a unnormalized, maximally entangled state. So this phi plus essentially says, okay, we have some orthonormal basis of HA, similar one for HA prime, and we send 1/2 of this entangled state through our operation E, and the other half is acted upon by the identity. In fact, I think I've got my notation slightly wrong. I would say identity on A, and then HA prime goes through E. So we end up with a state on HA, a linear operator on HA tensor HB. There are various ways of writing in this Tory operator with slightly different properties. So there's some that are basis dependent, some that are basis independent, but I'm sort of pushing those considerations aside for this talk. Some interesting properties of this resulting operator, so the non-calligraphy E that's written on the slide here, is we can map properties of the channel E, map the calligraphy E to properties of this non-calligraphy E. So for example, if non-calligraphy E is positive semi-definite, this is the case if and only if our original map is completely positive. And we have some trace condition where if we trace out over the target space B of this non-calligraphy E, then in the case where our calligraphy E is trace preserving, we will get the identity operator on our original space H of A. So these are nice ways of characterizing. So CPTP maps are calligraphy E via properties of their corresponding Toy operator. And this is important for the next slide. So you should now be able to see the quantum combs slide, where I've also written, also known as process tensors. And this is something that I wanted to point out properly, because I tend to use the terminology quantum combs, but there is a lot of work also under the formalism of process tensors. And as far as I know, there's no consensus on exactly how these relate, but they're very, very similar. And so it's worth knowing that both of these names exist, and to look in the literature of both fields, or both areas. Okay, so what is a quantum comb? It is essentially the Toy operator of a series of channels where there is some memory, there's some system that is pushed between each of the sequence of channels. So how is this formalized? Well, okay, firstly, we need a positive semi-definite operator. So C, the comb, is a positive semi-definite operator because we need things to be completely positive in general. We have sort of an iterative trace-out condition like we had on the previous slide. So this middle dot point, which has TP, trace preserving, in brackets next to it, this is essentially saying that for each channel in this sequence, if we trace out over the output space, we have identity on the input space plus all of these other stuff before it. So it's backwards iterative from sort of the final output space of this comb all the way through to the first input space. The terminology, or the notation I start to use for the set of combs is written at the bottom, where we have A1 in, A1 out, AN in, up to AN in, AN out. This is sort of saying something about the input spaces and output spaces of each of these maps, but not including the thing that gets passed between the sequence of channels. Again, please ask me if anything's not clear. So this bottom condition of these 3 dot points is essentially saying well, we can either have a normalized comb, which is when C0, the final thing, is equal to 1. So you do all these traces out, and ultimately we get a scalar 1. Or we can have a slightly more sort of probabilistic version where C0 is not 1. I mean, we still want it to be greater than 0, but it could be between 0 and 1, which means that something non-deterministic has happened. One of the channels has been non-trace preserving. For those more interested in category theory, there are some definitions floating around of quantum combs, or sorry, not necessarily quantum combs, but combs within various categories. So I mean, you can recover the quantum comb definition in some regards if you take your category to be appropriately quantum, but I guess exists more generally. And one example is written at the bottom here, where we use, I guess, Cohen calculus and various other things, which I really don't know so much about. Initially, I had references on these slides, and this was meant to just be a pointer to one of these references. The name, I guess, for this definition that you should look up if you're planning to do so is Mario Roman.
Just to note that the slides with the references are on the conference festival webpage. Yeah, I'm just looking at. Yeah, I hadn't seen this notion of a comb.
Yeah, so I guess I can make some comments about this. The terminology combs in the quantum information literature has come about, I think, in about 2008, 2009. The one key author that you can search for in this space is Giulio Chirabella. But then I guess the category theoretic one, I think, is more recent, probably sort of 2012 or 2015 or so. The process tensor framework, I think, is also around 2012 and onwards. So yeah, I guess it is a relatively modern phenomenon. I can also, I guess, talk about this on this next slide. So I have quantum combs and related and some applications. So again, and related here means not necessarily just the quantum combs formalism, but including the process tensor formalism. From the category theory side, these are used in various forms in quantum category theoretic machine learning. So CTML there is meant to stand for category theoretic machine learning. Again, I'm not so well read in this area. Some names you can search for are Bruno Gavranovic. He has, and Dan Schiebler, I think they have some paper where they essentially go through various category theoretic notions of machine learning. And in fact, I think DeepMind had a seminar series late last year that was essentially on category theory for machine learning. And yeah, some of the buzzwords within that are optics and lenses. And I, again, don't know what these are, but you can search for those if you're interested. I know Dan and I guess Will, I'm not sure if he's in the audience, but are interested in some logic aspects of quantum mechanics and other things, computation. And these, so quantum combs essentially have been thought about in this context as well. So there's a paper by Alex Kissinger and another author whose name I can't remember, where they talk about star autonomous categories. As far as I can tell, it is using a comb construction. I don't know if they specifically use that terminology, but as far as I understand it, they are, and they relate this to various notions of linear logic. For some more, I guess, physically motivated examples, the process tensor formalism has been used quite a lot and quite recently in terms of characterizing non-Markovian noise in quantum systems, so physical devices. Non-Markovian here kind of means something like, well, maybe Markovian, the notion of Markovian is familiar to people, where essentially this lack of dependence on your current time step of the entire history prior to this time step, whereas non-Markovian means that, okay, you may have some non-trivial dependence on all of the steps leading up to your current state. The picture on the right, the little sort of graphic, comes from a paper by first author Greg White, who's well, I think currently still a PhD student at the University of Melbourne in the physics department, where they use this process tensor formalism to analyze quantum computers from IBM in various ways. So if you're interested in hearing more about that, I do highly recommend you speak to him before he crosses the river and heads down to Monash for a postdoc. Definitely worthwhile speaking to him. All right. So the next slide we have is min entropy and the guessing probability. This is essentially the last slide we need before I can start to point towards some work that I've been involved with. The min entropy comes from, well, so it's an entropic measure, the name suggests, and it comes from some work specifically in cryptography and things like this. So again, I don't know if Eleanor is in the audience. I believe she's giving a talk a little bit later, and as far as I understand it, she works a bit in cryptography. One of the, again, as far as I understand it, her supervisor has worked with another person at ETH called Renato Renner, and he is one of the key authors if we're talking about min entropy. So you can look for that via his name if you'd like. But essentially, it's defined as you can see on the screen, on the slide. We have some bipartite state, and we're essentially trying to find out information about one of the systems, HA, by interacting with the other one only, HB. So the definition, HB and A given B of rho, there as the minus logarithm of this minimum thing, is maybe not so easy to interpret in that form. It's nice because this can be formalized as a semi-definite program, so it's amenable to computational approaches. I think the most so the intuitive way of understanding this entropy is given in the second half of the slide. So it has some relation to the maximal overlap of, so okay, we have our state rho, we're maximizing over CPTP maps E that map rho, so acting only on HB to another system A prime, such that this identity map, tensor with our E map of rho, has the maximum overlap with the maximally entangled state. So essentially, we're trying to find how much entanglement can we generate from our initial state rho if we maximize over all possible CPTP maps acting only on HB. I'm hoping that this equation looks a little bit familiar because it has this maximally entangled state in it. This time it is normalized. Before we had it not normalized, but there is a close relation to the Choi operator here. And this is a nice little trick that they use in the proof of, this equivalence between the min entropy and this fidelity term. The F there stands for fidelity.
I'm a little bit lost here. So what are we doing when we maximize this?
So in this current form in the middle, they're asking, okay, how much entanglement can we get out of our current system? Maybe I could talk about this last part, the guessing probability, because for me, this is the most intuitive. If one of our systems is entirely classical, we're trying, basically this min entropy gives you some quantity that tells you how much can I learn about this classical variable x by interacting with this other part, this quantum part that depends on x in some way. So if you look at rho xb here, we have this classical variable x, so p of x, x ket, x bra, and some quantum state that depends on x, so some series of quantum states, one for each x. And we're trying to figure out what x is. We're trying to figure out the value of x. The min entropy says, okay, how much certainty can I have about the value of x? But if you have the quantum case, it's, okay, how much correlation do I have with the system A instead of X?
Mm-hmm. Yeah, thanks.
Sorry. So yeah, when you have one of the systems classical, it is called the guessing probability because it's the maximum probability, or like, yeah, the probability that you will get the correct answer under the optimal strategy. And so this maximization form and the minimization form of the min entropy here reflects this notion of strong duality of the semi-definite program. So often semi-definite programs can be formulated equivalently as a minimization as well as a maximization. Okay, so I see that time is running on, so I think maybe I need to speed up a little bit. Moving on to the slide, the Combin entropy and the classical quantum combs. This is where I can start the point to work that I've been involved with. So the min entropy I just talked about in the previous slide is for bipartite states. So again, basically single time or two time correlations, because we're talking about maximizing over CPTP maps. But as we saw earlier, CPTP maps are not quite sufficient if we want multi-time correlations. And so accordingly, there's been a min entropy developed, or an analog of the min entropy developed for the Combs case. And it's essentially the same thing. So we still have this minimum form, we still have this maximization form, but instead of maximizing only over a CPTP map, we maximize essentially over a comb. So, well, it's a dual comb. So in this case, instead of a bipartite state rho, we have a comb C, which is on a many-partite system. It's operated on a many-partite system. And we're trying to think about what is the maximum correlation we can get with this final system, this final output system, by interacting with all of the systems along the way in the optimal way. So it just extends this notion from the previous slide. We also can extend this specific case where part of our system, one of the systems, is classical. So again, we have this variable x, and we're trying to learn something about it, and some set of contingent combs, sigma x. I'm now looking at the bottom of the slide. This is one of the main things we look at in the research project of mine, where we're aiming to learn some property x by interacting with sigma x. Sigma x is going to represent our quantum system undergoing dynamics, and the variable x represents this unknown property. So I said right at the start, the broad aim of this work is to learn about the unknown property by interacting with the quantum system. This is the way that we're going to do it, this conjunction of classical quantum combs and the comb min entropy. The nice thing I think about this, apart from the fact that it has the SDP component, which is nice, but I will talk about some limitations of that a little bit later, is that in this maximization form of the min entropy, the thing we maximize over has a nice interpretation as this multi-time strategy. So we,
Sorry to interrupt you.
Yep.
Still processing this C, I guess. So as an example, I might think about taking a Hilbert space with a tensor product decomposition and measuring something on one tensor factor. Would that produce something like this? How do I end up with a state that looks like that?
So I mean, I see the column C is not literally a state. It has similar properties to a state in a sense. I guess the best, or one way you can think about this is for every time step. So okay, we have Hilbert space A1, and we have the environment. A1 gets mapped through some CPTP map, or both of it gets mapped to some CPTP map, which is A2 and environment, and I act only on A2. I apply a unitary, I apply a measurement channel, I do something with it, which gets mapped to B1, an environment. So the environment stays through this untouched by what I'm doing. Then this goes to another CPTP map, both of them. I then act on B2, I apply another channel, I do some other unitary, it goes to C1, an environment, this gets passed further forward. So thinking about Hilbert spaces through time rather than through space, this comb represents this whole thing, this whole process. So on the title slide, I mean, it's drawn in this way where I guess time is running from left to right, more or less. Yeah. And you see part of it, you act on part of it, it goes back through some other evolution, which involves this environment that, you know, something that I do at time step 1 may come back and influence time step 5, for example. So there is this memory wire that goes through these series of CPTP maps. And this is, I guess, why it's also used in non-Markovian context. Does that help at all?
Yeah, thank you.
Yeah, so I think think about E as a learning strategy or some optimal thing that I can do. Okay, maybe before I say, just going back to what you asked, Dan. Often, and I'm not necessarily, I don't necessarily like this way of speaking about it, but often people talk about these gaps in the comb. So the things, if you look at the picture of a comb where I can input channels, they talk about those as being labs. So I have my lab, some quantum state comes into my lab from somewhere else, I do something, it goes out of my lab, interacts with the rest of the universe, goes into somebody else's lab, they do something else. And it's then finding the correlations between all of this stuff that we can do only in our labs or locally in our labs. That's one way people talk about these quantum combs. And so E here would be, I guess, the total strategy of all the labs put together, where we can potentially communicate also between the labs. We have some, yeah, fairly complicated thing in principle. Okay. So yeah, the project that I've been involved with is about a little bit about, I guess, the general theory of classical quantum combs and the mean entropy, but mostly we focus on some applications. So the first application I'll talk about is blind quantum computing, specifically one protocol for blind quantum computing. Maybe I should speak a little bit first about what blind quantum computing is. It is a cryptographic protocol where some client has very restricted computational resources and they want to do some computation that requires more resources. So they access some company, some server that can do this. They have potentially unrestricted computational power. There's some communication protocol that goes between both parties. And in the end, the client comes out with the result of that computation. But if that client has, you know, economically valuable or sensitive information, they don't want this server to know exactly what they're doing and why they're doing it. So it needs to be encoded or encrypted in some way. And so blind quantum computation is, like I said, a broad term for these types of protocols. The one that we look at in this work is where the client is entirely classical and the communication between the client and the server is entirely classical. And it's using a framework of quantum computing called measurement-based quantum computation, which is something that my current supervisor was heavily involved in the early 2000s. So maybe I don't go through all of the details just for sake of time. You can ask me a little bit later. But generally speaking, the combs that we look at here are, well, the variable of interest that the server is trying to learn is the specific computation, sort of the pre-encoded version. And the way that it can infer this information is by interacting with the client through the protocol. So the comb here, it encodes the protocol given the specific choice of computation that the client makes in secret, and the optimal strategy, or the min entropy, quantifies how much the server can learn under this optimal strategy. If the min entropy then is greater than 0, that means that the server doesn't know this computation with certainty. There's still more to find out about this. And this is one of the results that we can show using this framework in our paper. So in a single round where we do the protocol once, the min entropy is greater than 0. It also stays greater than 0 if we repeat the protocol a number of times. And we have also been able to show through an example that the min entropy does change between number of rounds of this protocol, which is not something that had been shown before. And also the existing results of security for this protocol were only restricted to the single round case.
I don't quite follow what can you explain a bit more what this final inequality means?
The final one, so okay, so
numerical one.
Yeah, we showed that the min entropy strictly decreases in this case. So the client, the server can find out strictly more information when it interacts with the protocol twice rather than just once. So I mean, maybe Eleanor can speak to you a little bit more about this, because I'm not a cryptographic person. I think the usual assumptions they make around security proofs in cryptography are that you don't leak essentially any information. So first of all, this protocol is not secure because it leaks a lot of information even in a single round. It doesn't leak all of it, which is, okay, something, but it does leak a lot. And we can show that it leaks strictly more. Well, there's an example of it leaking strictly more between different number of rounds of this protocol. I think if you wanted pure, like fully secure protocol, you need to show that it doesn't leak some more than like the size of your like the bit string that you communicate to the server, something like this, and it doesn't change. Like if you want, I think they call it compositional security, or the computational cryptography, and I believe Eleanor's supervisor is heavily involved with that software, has been in the past.
Yep. Yeah, we had a seminar on that here, so I, in principle, know something about it.
Okay, so this whole, was it abstract cryptography business?
Yeah.
Okay.
Yeah,
I read into it briefly when I was, I guess, working in this part of the paper, but I never. So I think there is some work, what they call them causal boxes, which is in this realm. It's in the cryptographic realm, and I believe there are also links to the quantum combs here. But again, I don't know exactly what those links are. One of the slides in, I think, 2 slides time mentions this, I believe. So because there's a table that sort of translates between all these things. Okay, yes, I see time is running quite quickly. So the next application, very briefly, is related to quantum causality, quantum causal models in particular. I'm really interested in these things, and this is actually where this project started in some regards. Very, very briefly, classical causal models are a way of discussing, also used quite a lot in machine learning these days, and it's sort of some way of encoding the data generation process rather than just the statistical correlations within a data set. Mathematically, we can consider them as random variables on the nodes of a directed acyclic graph. The arrows denote causal influence of one node, one variable on another, and typically they're also assigned some functional relation between the parents of a node and the value of that node itself. As I say, they're what they're good for. They're often used as a way of considering out-of-distribution learning and machine learning. But the one that we're most interested in for this talk is the quantum version. where instead of random variables, we have now pairs of Hilbert spaces. So this is sort of in our comb, the inputting the input Hilbert space to our lab and the output Hilbert space of our lab. We still have a directed acyclic graph, and then the functional equivalent, the functional dependence between nodes is now quantum operations, CP-TP maps. I mentioned earlier that quantum combs and process tensors are very closely related. There is also a notion of a process matrix, which is, as far as I understand it, a process tensor or quantum comb where you relax the strict ordering, the strict time ordering or causal ordering to one that's just partial. So, sorry, a total, you're restricting it not from a total order, but you go to a partial order instead. And I think quantum causal modeling is really interesting because it essentially is an extension of the classical version, because classical version can't treat Bell inequality aspects very well. Okay, so the link to the work that we've done is that now the variable x that we want to learn about, the unknown property of the system, is the causal structure, and the quantum comb is some fairly artificial, in our case, quantum causal models. And by interacting with the quantum causal model, we aim to learn about the causal structure. The min entropy then, I guess, quantifies, again, how much uncertainty we have about what the causal structure is. And if we use the semi-definite programming approach, this often can give you an example of the strategy E that optimizes the min entropy, or gives you the value of the min entropy. And this potentially can be linked to, this potentially can be analyzed to understand what the optimal causal discovery algorithm could be in this specific case. And this is something for future work. Okay. I like it. I mean, so as I said, this is something I want to do more work on in the next few months. The causal models that we consider in this work are also related to measurement-based quantum computation. So that was the starting point of this work. So they're a little bit. Sorry, go on. I was just going to say that they're a bit artificial in the sense of, well, they're not so important. I mean, you can kind of think about measurement-based quantum computation without this perspective, but we do it with this perspective anyway.
So what does a learning algorithm look like in this case? I mean,
yeah.
I mean, usually in a causal model, I guess the parameters are in the p's, right? So the p of xi given the parent, so that's a parameterized model, and then you want to infer what parameters fit the data best. I mean, you're trying to infer the DAG itself, if I understand correctly.
Yes. Yeah. I mean, again, because our, I guess, example in this case was quite artificial. I think learning. So it's sort of a promise problem in a sense. We have some restricted set of causal structures, which includes also the functional dependence contained within them. And so by learning, I guess, one thing, if you learn the DAG, you learn also what the functional dependence is. So you're not learning the parameters of the maps between them because they're kind of fixed with the DAG itself.
Yeah. So in classical statistics, you would compare the free energies of these different DAGs in order. I mean, then theoretically, the one with the lowest free energy is the one you should choose. I'm just wondering, is that any different in the quantum case? Is there some version of free energy that you attempt to minimize over all possible DAGs, or is it just a different idea?
I have no idea. I mean, I've not heard this free energy perspective on the classical one. Is this where you encode this? You have some sort of like continuous optimization problem over DAGs. Is this along those lines?
Well, given that the DAG is a discrete thing, I guess you don't do a continuous optimization. You just think of each possible DAG as a model, and then its free energy is like negative logarithm of the partition function in the physical language, and then you compare this number across different DAGs. Actually, this is something we think about from the point of view of geometry. So singular learning theory tells you that to compute that free energy and to compare different DAGs, in principle you have to care about singularities of some associated geometry. So I've thought a little bit about that. So I find this quantum situation quite interesting. But it sounds like you don't think about it that way. How do you compare different DAGs? What's the... When you say DAG, you actually mean not just the graph structure, but also these density matrices.
So, I mean, in the definition of the quantum causal model by DAG, I do mean just the DAG in the usual sense. They do have these operators associated to the quantum operations between nodes of the DAG associated. But yeah, like I said, for the one example that we have in our paper, both of these things are related. So you learn if you learn the DAG itself, you know exactly what the operations between the nodes are just by the set of DAGs that we consider, the set of causal structures we consider, because it's a very restricted class. So in that case, yeah, it's merely just identifying which of the set is the correct one. So it's not then trying to figure out which DAG and function, the dependence between nodes fits your data set the closest.
Yeah. Okay. Maybe I'll take a closer look at your paper. But I'm interested to learn more about this.
Because I guess in principle, yes, the DAG space is discrete, but if you also attach the maps between nodes, then that makes it continuous, right? You could potentially have any number of combinations of these that match your data or approximate your data.
Yeah, that's right. It's just that then the kind of you're parameterizing your space of possible causal models. It's somehow like a disjoint union, right? Like for DAG G, you've got the different ways of parameterizing all the density matrices between all the vertices or whatever. And then for DAG G prime, they're not. You can't move from one to the other continuously, right? So then, well, okay. Yeah, maybe I'll let you finish and.
I think I will basically finish there. So the final few slides really is just like an outlook of future work. Mostly, I think I should just point out the limitation of this approach. Trying to do the semi-definite program for finding the mean entropy caused us a lot of problems because we could only do really small cases. I mean, the aim for in particular, blind quantum computation case was to calculate the mean entropy for a number of rounds. So then you have this tensor product of things, but tensor product of a number of Hilbert spaces just blows up really, really quickly. And so we ran into a lot of problems just numerically with this. And then I think that's probably where I should stop. The final two slides are, I guess, well, one of them just is a table that I've taken from a paper by Simon Mills and Kevin Modi. Kevin Modi is also in Melbourne, but at the University of Monash. Works a lot in process tensor framework. And it just sort of has a bit of a translation tool using the terminology in various subfields of quantum information theory and similar things. So if that's interesting to you or useful to you, please have a look at that. And the final slide is just some comments about why I think causal models are really interesting and useful for artificial intelligence. So I don't think I need to speak too much about that formally in this talk. We can discuss it just casually as we've sort of been doing in the last few minutes.
Yeah, great. Thanks a lot. I'll just go ahead and ask some questions, starting with me reading through this final slide.
Okay.
Yeah, a friend of mine at the University of Melbourne, Ming Ming, works on causal models, and precisely for the reason in this first bullet point here. Can you just outline, like, in what, why is quantum machine learning a thing? What does that mean? And so there's, like, can I
Okay.
play a? Go ahead. Yeah.
So why is quantum machine learning a thing? I mean, if this talk is not being recorded and nobody takes this too seriously, I will say it's a thing because, you know, it sounds nice, it's pretty sexy, it, you know, prints papers, goes well in grant applications. I guess, I mean, some of the initial work in the area around, well, there's this one algorithm, the HHL algorithm, which does essentially, you know, linear algebra quickly on a quantum computer, and then they sort of shoehorn some machine learning aspects into that. You have I guess, promised speed up there. People are looking for speed ups, quantum speed ups, like we are with anything in quantum computing, any algorithm. People are looking for an advantage, and yeah, people definitely do this also in machine learning. There are some, I guess, fairly rigorous mathematical results that say in some cases we do have a speed up. There's been debate about other results that people have claimed speed up and then, you know, get disproven. So that's one general branch. I mean, as I've alluded to a little bit, specifically in the causal models case, I mean, I can also explain it a little bit on this slide. So the third point here, there's a bunch of explainability measures, I guess, related to causal models in the classical version, but they typically rely on having an accurate causal model for your data, and some of the guarantees around them go away if you only have an approximate one. And if your data essentially encodes quantum correlations, then, well, by Bell's theorem, you're not going to have a classical model plus classical probability theory that accurately describes this. So this is one reason why to go to quantum causal models. That's not necessarily an argument for doing quantum machine learning. It's, I guess, the argument that I like the most because it's my current bias. But generally, I would say quantum machine learning is based on the hopes of quantum advantage and computational speedups.
Mm-hmm. But presumably you're trying to learn about an unknown quantum state that maybe is generating some measurements that, I mean, one way of framing normal machine learning is to say that there's a statistical process, there's some sort of generating process, you have observations about it, and you're trying to infer what the process is. But when you're doing quantum machine learning, so I guess the process is quantum, the data is observations, or the data is actual states?
Yeah, so this is a good point. So I guess there are a couple of different ways to think about quantum machine learning, and one of them is where the data itself is quantum. But there's also a lot of quantum machine learning where the data is classical, and a big part of this is how do you encode this classical information into a quantum system such that you can then get this speed up computationally. And I think it is important to distinguish these two because they do have, I guess, different emphases and also different results relating them. In the case where your data is quantum, I mean, certainly people do look at learning of unknown quantum states. People also look at learning of unknown quantum processes, essentially to get around the whole tomography exponential blow up of
Right.
how many measurements you need to do. I mean,
Mm-hmm.
if you ever read about shadow tomography, this is a big part of this space. In fact, one of my colleagues here who's really into variational quantum circuits, which is, I guess, the quantum analog of neural networks, or can be seen that way, is essentially, well, one of the projects or one of the ideas he has is to see if you can have a variational quantum circuit that you train. So it's expensive. You train it over some period of time, but then when you need to like access it, you can just use these classical shadows. So you just sort of measurement outcome information, so all just classical information about this learned quantum circuit to then do something close to solving your current problem, which I think is an interesting idea. But again, I don't know where it will go.
Yeah, thanks a lot, Isaac. I
My
enjoyed
pleasure.
that. Yeah, I'll follow up with you and get some references about the quantum causal model stuff. I want to read more about that.
Sure. Yeah. I'm really into it, as I said, and I'm more than happy to speak about it anytime.
Cool. I guess we'll move over onto the next set of boards for Matt's talk. Let's give Isaac some thumbs up. Thanks, Isaac.
Thank you.